Welcome to this introduction on accelerated life testing. We'll be covering a few aspects of it. I'll be talking about, what it is, the fundamentals, some of the applications, a little bit of the science, and some common pitfalls. So there's two critical questions to answer about any product with regard to reliability. And this isn't just for accelerated life testing. This has to do with the approach to reliability in general for a product. So if we look at the definition for reliability, it's the probability an item will perform its intended function under stated conditions over its useful life. The two most critical elements here are the probability it'll perform its function. This is the failure rate during use life, which usually when we use the word reliability, that's what we're talking about. And then when does the useful life end? In other words, when do the wear-out failure modes begin to become dominant? This means, that's the end of what we've promised. We've promised you a product with 99% reliability, but that's not going to be the case 20 years from now. We may say that's for 5 years or 10 years. So the reliability during use life will vary, and what we'll find is that we will study that and look to characterize it. But at some point, like I said, it ends. The good life, the life of a good product will end with wear out. So wear out almost to some degree isn't a failure. It's the inevitable conclusion of a product that worked correctly. Because there's no product that goes beyond that failure mode. When you have a tire that you've sold that's a 60,000 mile tire, there's none of those tires rolling around with 2 million miles on them. They've all failed at some period after the 60,000 miles if they've been characterized correctly and used in an expected way. So we have to reframe it that we're not talking about random events. This is a very predictable behavior if we understand it. So you can see here I've highlighted on the bathtub curve, which is one of our favorite educational graphics in reliability, the two things I just spoke of, the probability, which is the failure rate, which is effectively measuring the height of this line, how high it is, and the time to wear out. So those are the two elements shown here in this graphic that we want to characterize first. And the tools that we use to do that are specific to measuring and improving for that, but the ones we're going to talk about are using accelerated life testing to answer the question about what is the time to wear out. So when a product fails from wear out, like I said, it didn't really fail. This tire that has been worn entirely through, this is not unexpected. This is predictable. This is what will happen if you keep using the tire and nothing else happens in its life that causes it to be taken out of service. Because this case with a flat tire, this was unexpected. This is not a wear-out failure. This is the failures that contribute to that middle part of the bathtub curve and how high that failure rate line is. So like I said, to some degree, use life and the time to wear out is really a design characteristic. It's something that we set in our product specifications when we start a program. This actually really starts with marketing because they are aiming to create the maximum profit based on how they want to capture a certain market, and there's elements that will accomplish that. And it might be the time to market. It might be this product has to be released by February 6th or there's no point. If it's a Christmas product, you better be on the shelves by Thanksgiving or there's no point. There's a cost point that works for this product. Depending on the features and what other elements there are, cost point's critical. Nobody's going to buy an economy car for $70,000. That doesn't make any sense. It defeats the purpose. Those are customers that would prefer to have less features and technology to have a better cost point. And then there are the features that we want to include. What does the customer want? Is Bluetooth critical? Handheld features, 3-axis motion if it's robotic. And then of course, how long are they expecting to use it? Is this a product? Is it a Christmas toy where we're expecting 90% of the kids to be bored of it in 3 months and it doesn't matter? Or is this a vehicle that customers are expecting to use for 10 years? And so what does that mean? That means that within that 10-year period, wear-out failure modes are not becoming a dominant behavior in the population. There might be a few that wear out a little bit prematurely, but we've looked to minimize that as much as possible because we just want to have the random failures be what occurs and we look to minimize during use life. So we have to keep in mind the ultimate metric is profitability and market, and this is a part of that. So we need to set the goal and we need to characterize it. So I always like to include this overlay on the bathtub curve of several different common reliability tools. And at the top you'll see I put a bar that goes from improving reliability to measure reliability. And that's because all tests can really be characterized as some combination, a ratio of their objective is to measure reliability and improve reliability. You'll see on there I have halt testing entirely on the improved reliability side. It really doesn't do a lot for measuring reliability. We have reliability growth that's in the middle. And then we have accelerated life testing. It's almost entirely measuring. And I've pointed on here as well where they typically address or use with regard to how we want to improve the bathtub curve. So we're going to talk about accelerated life testing. So what we want to take away from this is that this is entirely about measuring. There's not a lot of information you get out of accelerated life testing that you use to improve a design. You improve a design when you understand failure modes and what's causing them, but that's actually the input for accelerated life testing. You can't do a good accelerated life test if you don't already understand the failure modes. What you're simply looking to do is to measure when they occur under specific uses and specific environments. So let's keep that in mind. We're looking to measure here. That's what's important. And what we're looking to do is measure for the purpose of being able to characterize on the bathtub curve here when it's going to start turning up and we can no longer count on those failure rates during use life. So there's different things we need to know about this to approach it. We need to start by understanding the relationship between the stresses and wear out failure modes. So why is this so important? Well, this is so important because we need to know what model to apply. We are going to be taking that relationship between stress and wear out, and we're going to be increasing the stress and compressing the wear out. So that's not linear. That's usually exponential to some degree. If we have not correctly characterized this and adjusted our factors and our equations for it, we can be off by a tremendous amount because you have to remember it's exponential. Any small error in the trajectory on that relationship is very large later on. So you might have a product that thermal energy is the primary driver for wear out. And you might be able to, based on the model that you use, increase the temperature in test by only 10 degrees Celsius. And that quite possibly could cut the life in half. That's 10 degrees, so plus or minus 2 degrees will have a tremendous effect. Or having the factors in your equation being off by even a little bit could have a very large effect with how you translate the actual measured values to what will happen in the field. So it's rather sensitive. So we need to make sure we don't rush into what models we select and how we apply them. So some common models are the Arrhenius model, the Kauffman-Manson model, and then the inverse power law. And the Arrhenius model is very much based around the idea that temperature and material degradation will drive failure mode, and the Kauffman-Manson's around that temperature transition will drive failure mode. And then the inverse power law is a relationship where you can put a lot of other types of stress and failure mode relationships into and derive the compression factor. So we want to start off by saying what is our primary wear out failure mode, because there's many wear out failure modes, but there's one that we have to study them individually. So of course we want to start with the one that we believe is most likely to come first in the life. We want to know the stresses that drive it. Can the degradation be tracked? It may, there may be a clear relationship, but it may be something that's difficult to actually measure. And then can we accelerate the relationship? So something that's really important here is the different, we always talk about the physics of failure, but we use that term very broadly. I think it's important to distinguish between the difference between physics of failure and chemistry of failure. So physics of failure is mechanical failure modes that can occur. So this is usually fatigue, and degradation in how parts are interacting or handling stresses. And then chemistry of failure is when material properties are changing, and that's what's driving behavior change. So I mentioned the Kauffman-Manson and the Arrhenius model. The Kauffman-Manson model is based on the idea that the temperature cycling, going from hot to cold and back and forth, is what's driving the failure mode. And that's a mechanical stress because it's thermal expansion coefficients that are causing the parts to expand and contract in different ways. They can create tremendous mechanical stress, or even in the same part, if it's a very thick piece, you'll have big thermal gradients, and those thermal gradients are creating internal mechanical stress. The chemistry of failure, the Arrhenius model is looking at how materials change, their chemistry changes based on interactions usually with oxygen or salt or other things like that can change the material properties. And then if it's an electronic component, this could change the dielectric properties or how things insulate, or the other very precise combinations that are there so that those components have electrical properties. So the Arrhenius model, by increasing temperature during operation, will accelerate the rate of that interaction and those materials breaking down. We usually characterize it as breaking down. So I think it's very important to clarify that language and bring that resolution of the difference between physics of failure and chemistry failure, because this can have a big impact in how we approach the model we're going to apply. So where do we start? How do we start this complex process of creating an accelerated life test? Well, like a lot of places, let's start with our FMEA. Because the first thing is we want to make sure that we're going to invest our time and energy in the understanding the wear-out failure modes that are going to be occurring first and driving end of life. Obviously, there's other wear-out failure modes, but they're much farther on. But the ones we want to study are the ones that occur first. And these have probably come up in your design, failure modes effects analysis, because, in that process, you are identifying a lot of different types of failures, and you are looking at what are the root causes, what are the effects, and you're going to discuss ones that are wear out. So if you're familiar with this process, you probably will have earmarked the ones that are wear out, so you can come back to them later when you're doing your accelerated life test and deciding which you want to approach. And so I highly advise that, if you're in a DFMEA going forward or other failure mode effects analysis, risk assessments, that you do bring this up and try to earmark it. Because DFMEAs, I always describe them as at their core, they seem very technical, but they're really a project management tool. Because the real output is, we know that there's lots of different things we can approach to try to understand in failures and improve. But which do we go to? That's why we're doing the risk analysis, so we can prioritize, rank them, and apply our resource of engineering time and schedule until we run out. And so we want to do it to the things that are of greatest risk. The DFMEA, produces a quantitative way to measure with the risk priority number to do this. So with the wear outs, it's a great way to approach the ones that you think will be dominant. Another one is halt testing can be a really great way to identify some areas you want to look at for accelerated life testing. Now you saw there on very different extremes of that measure and improve, where I said halt testing's primarily objective is to improve and not measure, and alt is to measure. But that doesn't mean that you can't observe things in halt that don't inspire you to then try to pursue to measure. So you might see relationships in stress and failure and halt, and because of how the test is executed, you won't know much about that relationship with regard to how it might manifest in the field. But nonetheless, you will clearly identify that these vibration stresses, these temperature transitions, these elevated temperatures drive failure modes. And what you can do is design an accelerated life test now, knowing that you want to study those relationships, and now measure and characterize how they affect each other and if there's a degradation that leads to wear out. So that I think, there's lots of other areas to get, input for designing accelerated life tests. But those are two that I would say are very common. And of course, Others are the team looking historically to, like, you probably know a lot about your technology and understand the legacy products and designs and what's happened. And, a lot of that knowledge is what was the input for the design. You probably already have approached trying to mitigate, early wear out in your design. So that, of course, too, and having discussion with the team, a multidisciplinary team, can have a big impact, because each engineering discipline, whether it's electrical, mechanical, software, all see it from a different perspective, and they might think something is very obvious as a relationship that could be of interest, where another may not. So I very much encourage the first Xari Life Test approach in studying wear out to include a diverse team together, and sometimes a couple light bulbs go on in that process. So with Xari Life Testing, I've been doing it for many years, and have found a lot of the pitfalls, and I wanted to share some of those with you, because like anything powerful, it's equally dangerous. And as I described, with Xari Life Testing, you're generating a tremendous amount of information very quickly, which is very powerful. But that information is done through calculations that are usually exponential. They're exponential in growth, exponential in compression, which means very small errors get magnified exponentially. And there's also a lot of initial approaches and assumptions that can be done that can waste an entire program, because you've invested in something that isn't relevant. You've made assumptions that are not applicable. And if you're lucky, you find out before you release the product. If you're unlucky, you make big program decisions based on this, and you find out when in the field wear out failure modes are happening very prematurely. And that can be very devastating, because it's not just one or two units. Remember, this is a design characteristic. That means the entire field could start failing prematurely. You could end up driving to a 100% failure rate far before your intended life, and that can be very devastating. So it's very much worth taking time with Xari Life Testing programs, and taking time and being aware of what can go wrong too, to try to direct your behavior. So here's some of the common pitfalls. So a product life statement, based on a model, like I said, is a lot of assumptions. And the first assumption is that you fully and correctly characterize the stresses that drive the wear out failure mode. So keep challenging that. Don't just take the first thing that was selected, the first thing that was said, what somebody else has decided their characterization is. Keep questioning that, even through the program as you're building forward. Because yes, if you decided to characterize it differently midway through the program, that's unfortunate, but it's much less unfortunate than doing it at the end of the program or not at all. So to some degree, things like motorcycle racing are, you could say, are Xari Life Testing, right? You're running a device at a much higher level than you would normally. Can you simply extrapolate that out to the types of stresses and issues that would occur in the field, in a customer's hands? Do they, can you simply say, oh, okay, every mile in a race equals 1,000 miles in a customer's hands? Does that just work as a baseline? I mean, I think it's quite obvious that you couldn't do that, or just say that simply, because of how everything is used differently. I mean, take something, there's lots of stresses here that in a race are not accelerated at all. Maybe how the fuel is consumed from the gas tank, that doesn't, that's going to be whatever's going on in there is not really changed. It's still just going through cycles of tanks. So, you go through two tanks in a race, that's no different than going through two tanks in the field. But where, of course, things like tires are taking a tremendous beating with much higher loading forces, can you find a way to say that, in fact, 1 mile of tire use on a racetrack equals 2,000 miles of use on the road, where the under a use case you've defined as normal, where the acceleration, braking, and turning forces are much less. So we can't just throw a common scaling factor for what happens in a test in the field. We have to give it much more resolution than that. So we do want to determine what is the bike's life, but like I said, that comes down to characterizing very specifically the wear out failure modes that are dominant. We're not going to be studying the bike, we're going to be studying the specific wear out failure modes. And we have to make sure we're studying the right ones. Sometimes in intense testing, there's stresses that are not applicable. We have to understand the physics of failure, as I said. And you can root cause the failures of a failure that occurs in tests as much as you want, but it may not be applicable at all. I mean, in this case, in most things that you race, there's accidents and collisions that occur, and the race continues in a lot of cases, or they do repair. Would this be immediately applicable when you had a failure mode, for a bike and you tried to translate it to the field? You can root cause the hell out of it, but the use case that's applying in the accelerated test doesn't match or can't be correlated to the use case that you want to make a statement on in the customer's hands. So it's about the resolution of it's about looking at a fine enough granularity, and resolution of what's occurring. We're never just looking at the product, we're really studying the failure mode and its relationship to a specific stress. We need to make sure that we have clean data sets. So what do I mean by clean data sets? When failures occur, we typically bucket them in the 3 categories in the bathtub curve: infant mortality, use life, and wear out. And you can see here, I've added, whenever I show the bathtub curve, I often add those 3 sets of dotted lines you see at the bottom, one being quality failures, one being use stress, and one being wear out. And on there, I think that's important because the composite of the 3 is effectively what the full bathtub curve is. And it really highlights where they have, where they're driving the primary behavior for the population. Obviously, quality failures tend to show up much earlier and, have a much smaller influence later on. And wear out failures should not be occurring earlier and begin to influence behavior towards the end. So why am I making a big deal about this? Because if we're looking to characterize a behavior, which is typically what we do with data sets and statistics, we have a behavior we want to characterize so that we can then make predictions about the future or to see what would happen with different inputs than the ones we had for our data set. So we're characterizing a behavior. So we have to make sure the data we have is only from that behavior. So we want to, in accelerated life testing, only use data from wear out. That means we've root caused it from wear out. As you can see here in this bathtub curve, at any given point in time, any of the 3 types of failures can occur. So we don't want to be taking failures that are characterized as stress-related use life failures and including them in the wear out failure analysis, because that's going to skew the actual characterization and it will no longer be representative of wear out. Just because the use life failures occurred later in life, that doesn't mean they always will, right? Because they are not always time dependent. They can be just from a constant hazard rate and it can likely to occur equally at any time. So it's important that we do a really good root cause analysis process and we remove any failures that are not considered true wear out from the data set we're using to characterize. So, and it may be things that you don't expect. I mean, something like a motorcycle is, we think about the tires, the motor, big mechanical components. But the primary wear out failure mode could be, the wiring harness. It could be the connections. And the wiring harness might be why a lot of bikes' life ends is, electrical gremlins would be what the customer would observe. And they can be frustrating enough, even though that they're simple components, that customers decide that's the end of the product's life. So, how do we test that? What do we do with these? They're internal there, and would that motorcycle race accelerate it? I would say probably not. That probably would not be. You wouldn't say that 1 mile in a motorcycle race for a wiring harness equals 1,000 miles in the field. It's that would be a very difficult correlation to do, or really probably any correlation to wiring harness failures. So maybe we decide that it's the duration, engine heat and the duration of it that's driving a brittleness in the connectors that they then will break under just the vibration load. So we can say that we could use the Arrhenius model, which, if you recall, uses elevated temperature with the idea of not physics of failure, chemistry of failure, that the heat's going to increase the plastic's interaction with oxygen in the air, having it break, the plasticizers break down, and it becomes more brittle. So we'd say, okay, we can just do the Arrhenius model. We can take this wiring harness, we can put it in an environmental chamber, run it at an elevated temperature, take the Arrhenius, with the activation energy, and calculate out that these became, the point that we've determined is brittle, likely to cause failure. It happened in test in 4 weeks, and that equals 5 years in the field. But then let's say we do this and it doesn't match. Well, do you know what? There was another element here, UV exposure. So the UV exposure also breaks down the plastic, properties and can make them more brittle. And maybe we even had in the past done this and thought, had seen a really good correlation between the thermal and that. But those bikes we did it previously on had fairings. A fairing is a plastic covering on the side of the bike for aerodynamics. But of course it also blocks light. And this is more of this motorcycle here is more of what they call like a naked street bike, because you can see the engine, you can see the frame and everything. But of course, if you can see the internals, so can the sunlight. So you might find that in fact, just by simply making a wrong assumption that UV was a contributing factor, you could be making a tremendously inaccurate prediction as to when those connectors would fail. So it's very important that we don't just jump into accelerated life tests. A lot of times what I really like to see is time spent doing some explorations into the relationships. This can be very hard during the intensity of a product development program. There's always schedules and limited resource. If what I encourage is if some of your core technologies that are involved in a lot of your products, do accelerated life test programs that are separate from a specific product development program. Allow yourself the time to really investigate these relationships and develop tests that characterize them. The return on investment, not just in knowledge of what's happening in products, but in speed of product development, is tremendous. Think of how much faster your accelerated life testing programs go in a new product development program when you have fine-tuned and already set up and have previously done the tests you need to do. You can just jump right into them. But if you choose to do that without having done the independent research, like I said, anything powerful is also, equally as dangerous. So if you take a look at this bearing failure, it's very interesting. You can see where the fatigue was. They call that origin the spar, and then you can see where it's fatigued, and then you can see by looking at it when it failed, because you can see that it's much smoother, which is the fracture occurring very fast, right? That's where it's ripping apart. And the wear out failure mode here, by looking at this, they were able to root cause that it was oscillating stress that was excessive, causing typical material fatigue. And the reason why this ended up being a surprise, and they ended up having it in high volume in the field, is they were familiar with the Arrhenius model, which is the elevated temperature, and they had historically with their bearings found that the best way to predict life was to look at the breakdown of the lubricants, not the actual metal. And this worked very well in a lot of cases, because that was what the primary wear out failure mode was. It was the lubricants breaking down with that chemistry of failure over time from heat and their properties changing, and then once they fell beneath a certain level, now the mechanical fatigue would occur. But that was always the trigger. But with this other design they had less margin on how the actual physical stresses affected the material and its mechanical stresses. So that actually then became much more likely to be the primary wear out failure mode. The lubricant one still existed, but now this other one had a chance of happening first, and they didn't do any accelerated life testing to study it, because they just checked, they just knew, let's do accelerated life testing. And by just default going to the model they knew, everybody thought everything was okay, and nobody stopped to think, hey, wait a minute, we've actually should really be evaluating what's going on, because this design has changed enough that there could be other wear out failure modes that could supersede it.
Repeat that again, please. Wouldn't HALT find that?
Right.
bearing failure?
Yep. No, it not necessarily, but you have to remember with halt that you will find failures in halt, but you cannot make statements with regard to when they would occur in the field. You've made a trade-off, and the trade-off is this. With halt testing, in a very short period of time, with very few samples, you can learn about what failure modes look like. Usually in about 3 days with 3 samples, you can get to see all these really interesting failure modes that can provide a lot of really great design input for robustness. Well, that came at a cost, and the cost that came at is the stresses you applied were not in any way associated to any specific use case. The levels were not associated to a specific use case, and all of them you were going to keep stepping up until you saw the failures. So that's the price that was paid, and that's why the halt testing you see entirely on my scale of measure and improve on the improve side. It's outputting failure modes that are great for the design team, the root cause, and see if there's opportunity to increase robustness. I call it blind robustness improvement because you don't know how much you've improved it, but you've improved it. So the halt testing might yield a failure that's interesting, which is why I list it as one of the things that can be the source for the stress to failure mode relationship you choose to study in alt. But the halt testing is nothing more than a seed for the idea of what you want to pursue. The accelerated life test is where you'd actually measure it.
Good.
Yep, thank you. So here is the next thing is that you can have a lot of variability sample to sample, and usually in accelerated life testing you try to have a large 20s, 30s, 40s quantity that you're testing, because we really want to be able to draw a normal distribution, a bell curve, because there's natural variabilities, because obviously we're not looking to design a product that has a nominal wear out that's at the time our product's expected life to end. So in other words, if you design a product that you tell your customers is good for 5 years, you obviously don't design it so the wear out failure mode nominal value is 5 years, because that means 50% of your products are going to fail before then, right? That's a disaster. What you're going to do is you want to create enough data to characterize the wear out behavior, which should look like a bell curve, right? And you're going to have a mean and a standard deviation. So if your product's life is 5 years, hopefully the mean is more like 7 years, and you have a standard deviation where the tail, the left tail of that bell curve just barely crosses over to that 5-year mark. Maybe you say, okay, it's acceptable to have 0.5% or 1% fail and wear out for a big large population, and that's what we consider acceptable and we're going to design to. So we really only want that tail to be over there. Okay, this creates a challenge though, because what if we can't test a large number of samples because it's so expensive? Well, if we, like I said with accelerated life testing, it starts off with a very deep understanding of the physics of failure or chemistry of failure. So you might intentionally test units are on the far left side, the weakest units in that bell curve, where they're still within the manufacturing specification limits and would pass quality testing, but are much more representative of that left-hand tail that's so important to us. And so if you individually select or manufacture units that are weak in that area, you can do the testing with lower quantities and then do your best to overlay what you think the distributions are and where these would be, and make confidence statements that you believe the wear out failure mode, the nominals, the normal bell curve distribution is far beyond the lifetime that you're promising. So in this case, in this picture, there were premature wear out failures in the solder connections, effectively driven by overheating, and alt testing was done, but the problem is that it was done with the ideally soldered boards, and they did very few of them. And then when they got the variations on the they did the normal process later with the prototype boards. They did a process later of reducing solder to save money to within the specifications that were needed. But they didn't stop to consider that they just did testing on the prototypes that didn't have that dialed-in manufacturing process done when they were made, and they were effectively making wear-out statements on much more robust units. So let's keep in mind that, what are we testing? Are we testing what's representative of what's in the field? Are we testing what's representative of the variability, the natural variability in the field, so that we're characterizing the true mean and standard deviation of that wear-out failure mode, so we're making an accurate prediction of that left tail and how much it'll be within the use life. So the other element too is, are there other base stresses? Because like I said, this is very surgical and micro, where like with that wiring harness, I was talking about the very specific thermal and UV exposure to these very specific plastic components. You might even be able to do without the whole wiring harness and just the plastic, connectors. But are there other stressors that need to be there as a baseline? If you're studying breakdown from UV, do you need to have humidity and certain base temperature in there for the UV stress to correctly be degrading the plastic? It turns out that from my studies and work, I found out that humidity actually has a tremendous impact in how UV affects plastics. So we have to make sure those are there as well, and we're not, if there's a baseline conditions that allow this stress to wear-out failure mode to be correctly characterized, we have to make sure those are there. And sometimes there's more than one stress that is directly associated to the degradation, and this has to be considered in the model. And the acceleration model itself has to have more than one factor in it. Like I said, common pitfall, there's no such thing as small errors. Any estimation you make is an estimation, meaning there's some percentage of error you're accounting there. And it might be a level of estimation you're normally comfortable with in other tests where you're applying a use case and you're not extrapolating out to a magnified or a decreased version of the stress. But that same level of estimation in a model that has exponential relationship can be quite dramatic. So I find that a lot of times great and well-designed accelerated life tests don't support really helping what's happening in the field simply from estimations that then get, have large multipliers to them. So let's switch now to talking a little bit about one of the most common models so you can understand a little bit about how they work and what's going on. And this is me cooking onions, and instead of a recipe book, I have my accelerated life testing books. And there's a reason here, is because when you caramelize onions, which is cooking them at a lower temperature to bring out the sugars, because with the temperature, cooking is usually pretty much just driving increased interaction with oxygen for the properties to change. And in this case, sugars come out of it. You're effectively doing an accelerated life test if you were looking to predict what would happen to an onion sitting on the counter at room temperature. If you knew the activation energy for the Arrhenius model for the onion material, you would then be able to caramelize onions on a stove at a certain temperature and then use the Arrhenius model to say how long it would take for those sugars to come out of the onion breaking down on the counter. And that's how an accelerated life test works. It's that simple. And that's why we have refrigeration, because we're looking to slow that down even farther. And with that Arrhenius model and the correct characterization of the activation energy of the material of onions, I could then say that the sugars were able to be drawn out in 10 minutes on the stove at this temperature, which would actually equal about 3 weeks on the counter, which then if you lower the temperature further in the refrigerator might equal 6 weeks. And that's why we refrigerate food. We're looking to slow down what can be characterized by the Arrhenius model. But this is also really important to highlight two common mistakes that are made. Now, these onions are delicious when they are caramelized correctly, but I think you're quite confident you would not enjoy them as much after they've been sitting on the counter for several weeks. Why aren't they simply sweet and delicious? Well, there's a second wear-out failure mode happening on the counter, and that's bacteria breaking down the onion, making it rancid. So both things are occurring. The sugars are coming out of it as it sits there and interacts with oxygen, but there's also bacteria that is creating rancid materials. And this is not occurring in the pan. I've, by elevating the temperature, accidentally killed the second wear-out failure mode. I killed the bacteria. It's no longer part of the equation. The temperature didn't increase the bacteria's activation. It might to some degree for a few degrees, but at some point it kills it. So by correctly accelerating one primary stress to wear-out failure mode, I've accidentally eliminated another one. So if I made my predictions about what was going to happen on a counter for my cooking experience, they would be entirely wrong. Here's another one here where I'm demonstrating. I'm actually not that great a cook. You can see I've burnt some of the onions. So what I've done here is, because of the higher temperature, I've introduced another failure mode that doesn't normally occur, of burning, where now instead of the sugars just coming out naturally, I'm basically generating charcoal. I'm transitioning the onion straight to charcoal, because there's a point where the temperature has a secondary effect, right? I mean, think about plastic, the plastic with the elevated temperature. I can run it at a higher temperature to increase the rate to brittleness. You get over 90 degrees C, you might be melting the plastic, and that's entirely a different failure mode. So you can see from this some of the common pitfalls and how it all basically relates to each other. Now the next question I always get is, what is activation energy? You've heard me say that several times. Activation energy is the component in the Arrhenius model that is representative of characteristics of the actual material. And the best way to describe activation energy is, if you were rolling eggs along a tabletop and you're rolling them into each other, if you roll them very slow, they probably just bounce off each other. And then if you roll them faster, they will hit each other, break, and combine. Now the activation energy is the speed in which they would have to collide to cause them to break. So obviously different eggs, different thickness of shells, or different shapes, or different materials would have a different activation energy, which would require them to be rolled together and break. I mean, if these are billiard balls, obviously it's going to be tremendously high energy in comparison. So that's what the activation energy is. It's effectively a property of the materials that are involved in studying this wear-out failure mode. For most electronics, a lot of electronic products, you'll see like 0.7 EV is a common value or an initial assumption for electronic components, and the rate they'll break down. So obviously you don't want to run a test and just automatically use this, but for estimating the life, from a program perspective, this is a common value to use if what you're studying is, PCB boards and electronics failing. So as I said before, with these elements in these equations that are very specifically associated to the materials and the components included, what we want to do is validate our model. And a way to validate the model is to take our estimations for the things like activation energy or other factors that are associated specifically to the material, and to run them at 3 levels. And what you can do then is, from these 3 levels, is verify that those factors are correct, because they match what we know the degradation to be for a similar material. So as I said, this is a step that can take time and can be hard to argue to include in a program, especially if people don't understand accelerated life tests to that degree. And if there's opportunities to do this outside the pressure of a program, that's fantastic, because now you have these verified factors that can be used in a test that you can execute right away, and with confidence extrapolate out the real life. So in summary, how do we do an all test? We identify the failure modes using analysis and test techniques like Hall testing, the DFMEA, sometimes step stress, where we know a relationship between a stress and a failure mode, and we look to step it to see margin. These can all be great places to figure out what we want to start to study. We then want to characterize that stress to failure mode relationship. And in characterizing it, we want to make sure that the failures that we're studying, we've correctly bucketed them between being quality failures, use stress, and wear out. Because we want a clean data set. We're looking to characterize one of those 3 behaviors, and if we have data points from one of the other types of failures, we're not characterizing the behavior correctly, and our projections will be incorrect. We want to run bench tests to validate these inputs and performance. We've made a lot of assumptions up to this point. It's time to start to see if those assumptions are in fact correct. We want to document all the metrics and the ways we've been measuring everything and start to understand the health indicators. Remember, we're looking to the output is a measurement. So we want to make sure we're measuring the right things. We know how to measure it, and the equipment, that can be sometimes quite complex and take some time to develop to make sure we can measure what we want. We're looking to do it with a resolution to where we can characterize the degradation, not just the failure. It shouldn't be binary. It shouldn't be it's working and then the next second it's not working. Ideally, we can see a degradation. We can see how we're, what rate we're getting closer to the actual failure. Then we derive the accelerated life test model, and then we will validate the model with a 3-level test. And at that point, we should be able to go right into the accelerated life test and make our life prediction. So thank you so much for this. Please feel free to reach out to me with any questions, and I'll take questions now as well.
So Adam, let's help us by a sort of real world definition. Let's take a front wheel bearing in one of your Ducatis. It's not really subject to sunlight and it's only going to operate within the temperatures on which a rider can actually endure riding the thing. It will have very low axial force. It'll have considerable and very variable radial force if you're doing a wheelie or landing off a wheelie or like accelerating or braking. And it has quality of lubricant in it. Everyone follow that? So, and obviously speed will be a variable, and speed with load and without load will also be they'll be coupled at times and uncoupled at other times. So how do we design an accelerated life test for that bearing?
Okay, good. So the first thing to do is to look at what kind of margins you had for a mechanical system, right? Because you have the cyclical, stress to strain relationship, and do you have metal fatigue? Because a correctly designed metal part usually stays within the plastic range of deformation and doesn't have fatigue to end the life, right? I mean, most metal things that are cycled are designed in a way where they effectively have infinite life from the cycling fatigue. And so if that is the case and you've studied that and you see that, one, of course, you have to make that statement within a very clearly defined use case. There's people who, if they're out there doing wheelies and hitting speed bumps at top speed, and that's a different use case. But for the use case you want to make the statement, and that's applicable, I would then turn to the lubricant. What's that?
I want to make the use case for the most harebrained nincompoop who's going to ride the thing.
Okay.
Which means hitting speed bumps, etc.
Okay. So if that's the case, you have to decide as a manufacturer, you're going back to the product balance of grabbing maximum market share. Are you going to design a bike for that application? I mean, there are people that do that and it's intended. That's an adventure bike, right? That is meant to be both used on-road and off-road, hitting rocks, catching air, all that. Now, that usually will then drive a higher cost point because you're going to have to put bigger bearings in. You're going to have to, make it more robust to handle that. And that there's usually a cost to that. The cost could be it cuts out on its racing characteristics of being light, the unsprung weight is lighter. Or it could simply be, like I said, cost. So if that's your use case, again, you should be designing with considerable margin for that.
Okay.
Now, if instead it's an economy bike, a commuter bike that somebody's doing that to, you will have made the decision to not appease that kind of behavior, and then, so somebody does take an economy bike, a commuter bike, and do that with it, and it's going to wear out prematurely. They're going to have failures that are earlier. So then it comes down to how do you, from a business point, strategically handle that? Do you look to try to find indicators that that's what was done? Or do you just say, fine, that's just 1% of our market that we're going to lose? Most people don't do that. There's a lot of approaches. I mean, Apple had that with the iPhone. The iPhone's not waterproof, right? and people come back and say my iPhone stopped working. So they decided to be able to root cause that and measure it, and they put an indicator inside the phone that would turn red when they if water was exposed to it. So they could say, no, you exposed it to water. That's not the use case, right? If that's what you wanted, you should have bought a waterproof phone. So that's all about use case and market. But assuming that the thing is designed with the correct margins on it, I would say a mechanical bearing should not, the raceways and bearings should not fail unless there was a defect, some kind of spalling or something. So I would look to studying life based on the grease, and the oil that's in there and how that breaks down over time. And you're actually bringing up something interesting I didn't talk about, is that when you find wear out, there's actually 3 ways to approach, addressing it. One can simply be, okay, that's the end of our product life. That satisfies it. We had a 5-year product life. This clearly, the first wear out failure mode is beyond that. We're good. Or you do your testing and find out like, oh, geez, there's a significant percentage of wear out failure modes that happen before 5 years. 2 ways to approach that. The first is preventive maintenance. Can you introduce a preventive maintenance that then resets that wear out failure mode? So if it is grease, that would be why you repack the grease and bearings and don't throw out your cars, right? Or, nowadays they last forever, but back in the day, that's why you'd re-grease things, and that's why you change the oil in your car. You don't throw out your car when the oil's worn out. You redo it. And then just let me add one other thing. And then the other approach is to then, if that's not sufficient and you can't do PM, you then would try to re-engineer it so that lasts beyond the end of life.
So let's get back to accelerated life testing for that bearing. If we presume that its load capacity exceeds, it's overbuilt, it's not a mechanical failure, then how do we test?
So the way you would test that is if it's the grease and oil properties that are determining wear out. So in other words, let's pretend you had super grease, which is what's happened actually. You have these synthetic greases, the properties don't break down. Effectively, the bearing will go forever, right? If the grease was perfect, like it was brand new. So what you could do is study the grease itself. You might be able to even do it outside of the bearing. Just if you're able, that's what I was talking about, the right metrology and equipment, and if you can do they can do chemistry on grease and oils and tell you exactly the properties as they change over time. You might be able to simply put grease in a tray in an oven and bake it at a temperature, use the Arrhenius model to back that down to the temperatures you expect it to see in the bearing, and predict life. And obviously that's what they have done, because now they make oils and greases that are forever. You can actually buy lawnmowers and things now that don't have an oil fill hole or drain, because the oil will last in the lawnmower for 5 years. It's crazy. And and the way they've done that is through accelerated life testing on that specific thing that drives wear out failure modes. In that case, they had the more detailed you are, the more you learn. So that's the result of that work.
So while you're baking that synthetic oil, like getting that correlation to say, all right, well, it finally did change properties, chemical properties. How do you correlate that? It's sort of an abstract, but all these things are abstractions. How do you correlate that with that equals 10 years of normal life or something like that?
Is that what that equation is for?
Yeah, that's what the Arrhenius equation is for. And, so that's why I'm saying that that's something you wouldn't try and do for the first time studying grease within a product development program. That's obviously takes some work. And so the reason why we've come so far with it is a lot of people have done work independently of product development. Oil and grease are their own products. So, of course, Mobil and Exxon have these huge research labs that have been going for decades and decades and decades, and they've perfectly dialed in the Arrhenius equation for each specific type of grease, each specific type of, they can tell you exactly that electron volt, that 0.7 electron volt they put up for every single one of their products. And then they would do their testing and be able to extrapolate out, and they know what other factors there are that can affect it. There's a reason why they can tell you if you tow with your car instead change the transmission fluid every 3,000 miles instead of every 12, right? I mean, they've studied all that. They can tell you exactly that by the extra loading, the extra heat load, how much you've compressed it because of the activation energy, and telling you, in their case, they just say, change the preventive maintenance schedule. But that comes from that Arrhenius model.